In this session, we will solve a few problems which appeared in CSR November 2020 exam from Organic Chemistry. But the first question here is the order of the rate of decarboxylation. You need to predict the decarboxylation, uh, the fastest and the slowest decarboxylation after these three carboxylic acid compounds. So for that, we need to be first generate the anion after removing carbon dioxide, and this is the anion generated from this compound, and this is the anion generated from this compound after CO2 elimination and saying states. And looking at the stabilities of the anions, we can decide the rate of decarbonation. In this case, the anion generated is stable because of the presence of electron withdrawing nitrogen. It withdraws the electrons in a sigma fashion, thus stabilizes this negative charge. So it is formed quickly, and the rate of decarbonation is fastest in this case. The rate of decarbonation is slowest in this case because the anion generated is not stabilized by the presence of nitrogen. Here, this anion will get accumulated, the negative charge will get accumulated because of the presence of lone pairs of electrons, and that would involve in conjugation with this pi band and makes this negative charge even more localized. That is so it is not stable, so it is not formed quickly. So rate of decarboxylation here is the slowest. In this case, the rate of decarboxylation is in between these two compounds. Next problem is this. This is based on the Nazarov cyclization. In this case, we need to first make a 4-pi electrocyclic ring closing reaction using 4-pi electrons. This is the 2 electrons from this bond and 2 electrons from this bond. These are not involved because this carbon is slightly positively charged and this is not. This is negatively charged. So we'll take only these 2 pi bonds with 4 electrons. As no photochemical conditions is given here, we should take it as a thermal conditions. Therefore, in thermal conrotation, we will follow to cyclize this ring. So this is the this set of rotations will make the conrotation. Now we need to rotate the substituents at this sp2 carbon and substituents at this carbon like this. Now this is to be rotated in a clockwise fashion, and this also will be doing in clockwise fashion. So when you rotate this substituents in a clockwise fashion, this hydrogen will go down and this part will go up. That you can see here. As this is down, this should be above the plane. In this case, this would come up, this would go down, this has come down, and this should be taken as going down. And that's how we should rotate the substituents in a conrotation fashion to close the ring. And the pi electron reorganization here is this pi electrons through this carbon will make the bond here, and this pi electrons will go here, makes it double bond, and O will be O minus, and the positive charge is generated here. This compound, this positive charge is now here stable because of the beta silyl effect. Now this bond, this compound would lose a SiMe3 group with these electrons, this bond electrons coming towards this bond and making double bond to give you this final product. And in this case, this is an intramolecular aldol condensation reaction. In this case, 2 sets of reaction conditions are given. The first one is the basic condition at a low temperature, and second is the acidic condition. We need to condense, do aldol condensation under reflux conditions. Reflux conditions means under high temperature. So first this compound under basic conditions, what is done is a less substituted enolate is formed. A less substituted enolate is formed by abstracting proton present here. Then we should abstract the proton here, generate the less substituted enolate is what generated under first conditions. Then we will condense this carbon with this carbonyl group, and this carbonyl group will be condensed with the NH2 group, will give you this product. In the acidic conditions, it is thermodynamically controlled product is formed. In this case, the more substituted enol is formed. The more substituted enol is formed by removing this proton. We can generate a more substituted enol, then condense this carbon with this carbonyl group and this carbonyl group with this NH2 to give this product. Overall, what you can see is the condensation of this CO group, this NH2 is common in both the cases, but under basic conditions, this carbon will get condensed here, and under acidic conditions, this carbon will get condensed with this CO group. With the elimination of water, will get double bond. That's how these two products are formed. And in this example, what is given is a substituted cyclohexenone is there, and the first set of conditions here is triphenylphosphine and tertiary butyl silyl triplet is given. The next site is a strong base butyl lithium is given along with the electrophile butanol, aldehyde, and finally a fluoride donor. So when you write this cyclohexenone, and this triphenyl phosphine adds onto this alpha beta unsaturated cyclohexanone in a Michael fashion, because you can take this phosphorus as a soft nucleophile. This carbon is a soft electrophile. You can have two electrophilic centers in this compound, and this can be one electrophilic center, and this can be one more electrophilic center. But this carbon is slightly soft in nature, and this is slightly hard in nature. So as soft base would prefer to bond with soft acid, a soft interaction would make this triphenyl phosphine to add on this side. So you will get this. It uses its own 5 electrons, makes bond with this carbon, and this 5 electrons would come here, and this will be O minus. Once this is formed, this O minus enolate will be trapped by this trimethyl tertiary dimethyl silyl triplet in this fashion. Electrons will go here in silicon, and this OTF will be left as OTF minus. Once this is formed, now this butyl lithium, a strong base, would abstract the basic proton here, generate the anion. Once this is formed, this is a good substrate. This now is a substrate for doing Wittig reaction. Doing Wittig reaction with carbonyl compounds. In case of aldehyde, it's more even more faster. It would give you the alkene here. So this carbon and this carbon with the elimination of triphenyl phosphine oxide through the known mechanism in the form of a four-membered oxetane ring, you'll get alkene is formed. And when in presence of fluoride, this fluoride would deprotect the silicon reagent, and the electrons present on oxygen after decellulation would come onto here, makes it a carbonyl group, and this pi electrons will come here, makes it double bond, and this pi electrons through this carbon will get protonated after workup and gives the final product here. The next example, this is an example of intramolecular cyclization reaction. This is based on hard soft acid base theory. And now here in this, the first example, the nitrogen is a nucleophile, a hard nucleophile. A hard nucleophile would prefer a hard electrophilic center. This carbonyl carbon is taken as hard electrophilic center compared to this carbon. So though both are electrophilic in nature, this is hard in nature. So this through its lone pair of electrons present on nitrogen, it makes bond with this carbonyl carbon with the elimination of earth oxide to give you this compound. And in this case, a sulfur nucleophile is there. Sulfur is taken as a soft nucleophile because it's of a bigger size. The negative charge present on will get completely stabilized or delocalized. So it will be taken as a soft base. Soft base prefers soft acid, or a soft nucleophile. It will go to soft electrophile. This is the carbonyl carbon. This is beta carbon. With respect to this carbonyl group, it makes bond with this and these electrons. Again, it will go on to the enolate, and coming back onto the ketoform will get protonated here at this side to give this compound. And that's all is about this video.